from now on, I will be describing some theoretical aspects of black holes. And so black holes have very interesting conceptual aspects, and understanding these aspects will be very, very interesting. Now, black holes have some interesting properties. The first one is their universality. So the final shape of the black hole is independent of how it was formed. So the final shape of the black hole is determined by 3 parameters. One is the mass, the other is the angular momentum, or the angular rotation velocity, and also it could be its charge. And this is a bit surprising because, I mean, for stars can have all kinds of shapes and all kinds of colors and all kinds of chemical compositions, and they're very complicated objects. On the other hand, if all these stars collapse into a black hole, if they were to collapse into a black hole, they would collapse into black holes which are all essentially the same. Now, I cheated here. All these stars are pictures of the sun, but and now another interesting property of black holes is the following. So imagine that we have a black hole collision, like the ones that LIGO, that the gravitational wave observatories saw. These black holes have some initial masses, and therefore some initial total energy, given by Einstein formula equal to mc squared. These black holes collide, and they emit some energy. They emit some gravitational radiation, right? So the final mass of the black hole will be smaller than the masses of the original 2 black holes, right? And so you might ask, could it be the collision be such that all the mass is emitted in gravitational radiation and almost nothing is left over, right? Could that be possible? And the answer is no, because there is a so-called area law that Hawking discovered, which says that the area of the final black hole should be bigger than the sum of the areas of the 2 initial black holes, right? So that's an interesting property of black holes, and it's interesting because Einstein's equations are very complicated. So they deal with the intricate shape of the space-time geometry, and it's very difficult to solve them. Even with computers, they were only solved like maybe about 15 years ago. People only then managed to be able to solve Einstein's equations in a situation like the colliding black holes with a computer. But nevertheless, they have this very simple property that's very simple to state. And physicists always love these simple properties of complicated systems, right? So this is a very simple property to state. And it follows from those more complicated equations. Now, all that we discussed so far are properties of black holes according to Einstein's theory or general relativity, which is a classical theory. So a theory with equations such that if you say, well, we have a space-time with some initial shape or geometry, we can predict the future in a completely deterministic way. Now, when we include the effects of quantum mechanics, we encounter one new surprise, and it's the fact that we can have white black holes. So let me try to explain what I mean by this. So Hawking discovered in 1974, and this was probably Hawking's most famous discovery, that quantum mechanics implies that black holes emit thermal radiation. And the radiation that comes out of a black hole has a wavelength that is proportional to the size of the black hole. So it's roughly equal to the size of the black hole. So if you were to take a black hole and you make it smaller, and even smaller, it will get hotter and hotter. So the radiation will have higher and higher frequency, and we would see it hotter and hotter. And so we can calculate the temperatures for black holes of various masses. So for black holes that have roughly the mass of the sun, which are the types of black holes that are produced naturally in the universe, this is a very, very tiny effect. So these are degrees Kelvin, so degrees above the absolute zero of temperature. And this temperature is so small that it's swamped by some other effects. And so we have not seen, and we probably will never see, this effect in astrophysical black holes. Now, if you were somehow to have a black hole which has the size of a bacterium, that's roughly the wavelength of white light, then you would actually see it white, right? So it would be like a tiny white dot, and with your own eyes, you would be able to see it white. That would have to have a mass roughly of a continent. So it would still be pretty heavy, and so it's not good as a flashlight. Okay? Now, why do we have this? Why do we have this effect? Well, it's related to relativistic quantum mechanics. So it's quantum mechanics and special relativity implies that particles can be somehow created and destroyed. And however, when we have the vacuum, so you can have some particles that come out of the vacuum, but there is a certain law that says that there cannot be particles with negative energy. Okay? So if you have, momentarily you can have a particle with positive energy and one with negative energy, but only for a short time. There is a kind of policeman in the vacuum, in the universe, that always ensures that there are no particles with positive energy, okay? With negative energy. But these policemen are constrained by the uncertainty principle. So that says that you can have some energy. So if you measure you cannot measure energy very precisely over a very short period of time. So in order to measure some energy, you have to wait for a time which is longer the bigger precision you want on your energy. So for a very tiny instant, you can have negative energy because the policeman cannot measure an energy over such a short period. Okay, but then, and that's due to the uncertainty principle. And so in flat space, this negative energy particle has to immediately annihilate with the positive energy one, and there is no net particle creation. Now, in the presence of a horizon, there is a new thing that can happen, which is that what is positive energy for the policeman outside is not actually energy from the policeman inside. So that, because the spacetime is so distorted that the notion of energy inside is different than the one we had outside. And so this particle, which from the outside point of view has negative energy, from the point of view of the interior is a perfectly allowed particle. It just has negative momentum in some sense. And that's perfectly allowed. So the policeman in the interior is perfectly happy with this particle. And therefore, here this negative energy particle can go in, and the positive energy particle can come out, and we see it as Hawking radiation. So this is a qualitative explanation, and in the end, we have some net particle creation. The observer outside sees this flux of particles with positive energy. And what are these particles? Well, these particles could be photons, so the particles of light, and so we could see the radiation or light coming out of the black hole. So this implies that as it emits radiation, the black hole loses some mass, and therefore has some finite lifetime. So let's say what the lifetime of various black holes are. So a black hole of the mass of the sun or the mass of the Earth will live much longer than the age of the universe, so you will never see it disappearing. A black hole with an ordinary mass, say 100 kilograms, will evaporate very, very quickly. So I put here a millisecond, but it's even much smaller than that. So, and it would emit all that mass is converted to energy, to radiation, and so it would be a big explosion. It would be worse than a nuclear bomb. Okay? And a black hole of a mass of roughly a mountain could be produced at the beginning of the Big Bang and would be evaporating right now. And now, this is an interesting mass range because, I mean, black holes of the mass of a mountain are not produced in the current universe through ordinary astrophysical processes, but perhaps something weird happened in the beginning of the Big Bang and such black holes were produced. And in addition, maybe very small black holes might be produced in particle accelerators, but those black holes, if possible, would decay very quickly. I mean, this is a somewhat remote possibility. It depends on what the laws of physics are at a relatively short distance. Okay, so that's a quick summary of this Hawking effect and some of the implications. And now we'll see some very interesting problems that this discovery of Hawking raises. So the thermal properties of black holes mix quantum mechanics and gravity, and it leads to puzzles. I mean, classically, remember that classically black holes can only grow in size, so they can, so something can fall into a black hole but not escape. But these quantum effects imply that the black hole can lose some mass, so it implies somehow something different than what we see in the classical physics, and that's why that's part of the source of the problem. So I will discuss two puzzles. So the first one is, why are black holes hot? Why do they have a temperature? And the second is related to the information loss. So what is temperature? Now, we know since the times of Boltzmann that temperature is due to the microscopic motion of the constituents. So if you have air, for example, you have molecules that are moving around, and if you have cold air, they will be moving more slowly, and with hot air, they will be moving more quickly, right? So heat is due to the motion of those microscopic things. And so the question is, in the case of black holes that are also hot, what is it that is moving in a black hole? What are the constituents of a black hole that are giving the black hole its temperature? Now, there is a related thing whenever we have a thermal system, which is the concept of entropy. So entropy is roughly the number of possible configurations of those microscopic constituents. And the first law of thermodynamics that gives us the entropy if we know the energy and the temperature. And Hawking's formula gives us the relationship between the mass of the black hole and the temperature. And so we can calculate the entropy. And it turns out that the entropy is the area of the horizon in units of the so-called Planck length. So this is a very tiny length. So for a macroscopic black hole, this is a very high entropy. And then the area law that Hawking had discovered previously, before discovering this Hawking radiation process, becomes the second law of thermodynamics, which says that entropy increases. So second law of thermodynamics says that for any system, the entropy would always increase. And here it's manifested through the area formula. And this is a surprising thing because out of classical Einstein's equations, completely deterministic, you see this behavior that looks characteristics of thermodynamic systems. So what are the constituents of a black hole that give rise to this phenomena? And this should be related to the macroscopic constituents of spacetime itself, because it doesn't matter how black holes were formed. They don't depend on the detailed properties of the properties of black holes don't depend on the detailed properties of matter. They really depend on the properties of spacetime itself. And so that's why understanding black holes is understanding the nature and structure of spacetime. Now, the second issue that is raised by the existence of this radiation is the following. So we can form a black hole in many different ways. We emphasized this many times. But according to Hawking's formula, the black hole will emit radiation and will evaporate always in apparently always the same way, emitting this Hawking radiation with no information of what fell into the black hole. But in quantum mechanics, this would look a bit like a collision, where you bring in something, you form a black hole, and something comes out, right? So it's a collision that is not different from, at least conceptually, from far away, viewed from far away. It's not different than any other collision. And all such collisions in quantum mechanics, the final state should depend on the initial state. And so if we have a precise quantum mechanical description, then these thermal aspects should arise only due to an approximation. So it looks approximately the same, but exactly it should not be the same. And so there must be subtle differences in the outgoing radiation that reflect how the black hole was formed. And so one question is to understand, well, first of all, how to calculate those subtle differences, at least in principle, and how those subtle differences are imprinted in the radiation by the matter that fell in. So those are the questions. And in order to even attempt to answer any of these questions, we need a theory that puts together quantum mechanics and gravity. So it has to be some theory that can do that. And one theory that can do that is string theory.